Alright, so the first thing to note is it does not say perpendicular bisector. It does show that though. So I kind of said in passing yesterday that we don't trust the picture. And what I meant by that, it's okay to trust notation like a 90-degree angle. But we don't want to trust like, oh hey, it looks like AZ is about the same as JZ or something like that. So unless it says drawn to scale, which our pictures are almost never drawn to scale, don't rely on relative relationships, like saying, hey, those look congruent, so I think they probably are. That kind of stuff is no good. But like I said, notation, if it's notated in the figure, then yes, obviously we trust that kind of thing. So this is a segment bisector that happens to be a 90-degree angle. So perpendicular bisector in the end. AD is 24, AZ is 2x plus 4. So we know that it's relying on the segment addition postulate to solve, because we're saying AZ plus DZ, or we could say ZD, equals AD. So piece plus piece equals total. But the problem is we don't have an expression for ZD. We have 2x plus 4 for AZ, and we have 24 for AD. And we have this blank right here, but what do we know? Based on geometry properties, what do we know we can plug in right there? So this is where you go back through and you're like, oh, it's a bisector. I know the segment addition postulate, and you start filling information into your picture, which is this. What does bisect mean? Cut in half. So that splits those two into equal pieces. And then what can we fill in right here? For D. Yeah, 2x plus 4. Okay, so we get 4x plus 8. Then we get 4x equals 16 and x equals 4. It says find the value of x in this case. Remember, sometimes it will go back and say what is the length of AD, or excuse me, AZ or DZ or whatever. So just keep an eye on that back check that's plugging back in. How'd you do? Let's just do raise your hand if you got it, please. Let's do that. So hopefully you're starting to see this process. Geometry concept sets up an algebra relationship that you solve, and then go back to geometry mode sometimes to get lengths, angles, etc. That's going to be a continuous process all year long. So let's do a quick reminder. That's not it. There we go. Quick reminder of this segment addition, or excuse me, the perpendicular bisector theorem from our notes yesterday. Remember that it can look like a triangle as well. It can look like the big circles thing. There's just lots of versions of this. So what are your cues? Like, here's a Y shape, and it says an airport baggage inspector needs to stand equidistant from the two sides or the two conveyor belts. So is this I keep saying the wrong word. Is this a perpendicular bisector problem? That's what I want you to think about. The bells belts are in for the break. My question again, is this a perpendicular bisector problem? Okay, we'll answer that when we come back. So question again was, this baggage inspector needs to stand equidistant from the two conveyor belts. So from these two, he wants to park himself in a way that he's the same distance from both of those. Okay? So is that the perpendicular bisector theorem at work there? Okay, so again, we're training our eyes to look for the pieces of the theorem that we need. In the theorem, we said we had some line segment, and we had a bisector that happened to be perpendicular, and then we said any point on that bisector was equidistant from the end points. Does this picture look the same as that picture? No, not to me. Okay? So this is not a perpendicular bisector problem. We haven't actually talked about this yet, but we aren't looking at a line segment that is split by a bisector or anything that's perpendicular as of yet. We will here in just a second. Okay? So just want to keep putting those in front of you. That makes you like think through, okay, what conditions have to be met for this to be used. This is actually the angle bisector theorem. In other words, this will be bisected now instead. Okay? And we'll talk about that here in just a second. But let's check your homework. I had a question on number 12. So if you want to pull that out, we'll do it first and then check the other answers. I will assign you these kind fairly often because error analysis is a really powerful way to check yourself. Because if you can spot somebody's error in their work, it's helping you to learn at a higher level. So it says the student analyzed the diagram and incorrectly concluded that AB equals 2BC. Well, what does that statement mean anyway in English? Lyra? No. It isn't saying that because it has a 2 there. Here, I'll write it. Well, I don't know. Do you not have your paper? Okay. So for AB and BC to be congruent to each other, we would have to not have the 2. So what does sticking the 2 in there tell us, Tim?
That it's equal to like 2 BC, like BC times 2.
Yeah, it's twice as big, right? AB is twice BC. So AB and BC. Good to find them in our picture. Okay, it says EB is the perpendicular bisector. That tells us, let's see if we can not overcrowd this picture. That tells us that AB and BD are what? Those are congruent by the perpendicular bisector theorem because EB is splitting AD in half. So this one says AB, BD is congruent. Yes, that's good. Check. Okay, angle BEC and angle DEC are congruent. So let's remember our naming construct BEC, BEC. We're shown it up here that those are congruent. So that's not really a check step, that's given. So BC and CD must be congruent. Is that true? If these two angles are the same, do these two pieces have to be the same? So we'll put a question mark there. Just, I'm not saying you're right or wrong, that would seem to be a spot we weren't sure about. Alright, and then let's go check some more steps. BC plus CD equals BD. Is that true? It says this, is this piece plus this piece this whole piece? Yeah, that one makes sense, right? And that whole piece equals that whole piece. We already said that up here. Is that true? Is this part of the statement true? Yeah, we said it up here and we already checked, okay? So far, that line is completely fine. Okay. Okay, let's check the next line. BC plus CD. So again, just always go back to the figure. BC plus CD equals BC plus BC, which BC plus BC is 2 BCs. Okay? That line's logic is true only if this is true. And this truth relies back on this truth. So the logic here is okay as long as BC and CD are the same. Okay? So is that true? That must not be true. So do you see how you can kind of work through this logically? Yes or no? Okay. So there's the error. That is not necessarily true. This is a good example of what I was talking about. Just because they look the same doesn't mean that they are. Okay? So don't use pictures to say, oh, it looks like. No. Alright, any others that you'd like to do? By the way, I'm not saying that this isn't. I'm just saying that we don't have geometry proof that it is the same. Okay, so we have to be careful with that. So that's where the student made the error. Okay, any others again? Any others that you want to talk about before we just check answers? Can you close your Chromebook? Alright, so answers. We did 11. Did I give you 11? Okay.
Yeah.
So we needed the angle bisector theorem that we haven't talked about, so I'm sorry on that one. The answer is yes by the converse, but just ignore that one. And then we went over to 14, is that right?
Yep.
To 17. So 14 is 22. 15 is 3.5. 16 is 21. 17, 6.6. 16 is 21. Yeah, 21. So, any questions on those?
Seventeen.
17, okay. Alright. Take a look at that figure. Does it look like a perpendicular bisector figure? Notice there is no direction that says use the perpendicular bisector theorem, and there won't be when you're being assessed. So how do you know that that's a perpendicular bisector problem? Like, what about it stands out and says this is that? Like,
Like both the triangle or all three of the triangles are equidistant from B to D. Like I
okay,
don't know how to
I
explain
think I
that.
know what you're saying. Like these,
Yeah.
that. Okay. So he's recognizing those triangles. Here's another way. If I extend AC, and we already see that that's a right angle, like that looks like it's splitting BD in half. BD is the line that we're talking about, is being bisected, right? So it doesn't have to form lots of triangles, but it also can, like this one here. Anyway, so 17. If EB is 6.2, so I'm going to start labeling 6.2 there. CD is 3.3. And ED is 6.2 also. What is the value of BD? Okay, let me clarify something that's critical in geometry. This is going to be temporary. Right now, is there enough information to guarantee that it's perpendicular bisector? Is there, like Corbin said, these lengths are congruent? Are they? Do we know that just looking at that picture right now? No. Like, if, let's say we were in court, you don't have proof that those are congruent, do you? It looks like it's congruent, but it's not good enough to say it looks like. So starting there, this looks like a perpendicular bisector problem, but we don't have enough information to guarantee it yet. And in this class, I want you to think court. If it's not beyond a shadow of a doubt, it's not true. Okay? Now, when we put this information in there, do we have enough information to guarantee it? Yeah, now we do, because we have the fact that this is perpendicular, and we are told that these two are congruent now. Now we do have sufficient evidence that the perpendicular bisector theorem holds. So now we can use it. And it says, what is the value of BD? So now we know that BD is bisected, which means those two pieces are congruent. We know we can copy 3.3 there, and now we can just double to get 6.6. That is only true though because of those two being equal. If this said 6 and 6.2, we are stuck and cannot do the problem. Because there's a lot of subtlety going on under the scenes here that people just make assumptions and gloss over, and you need to not do that because it will bite you eventually. Okay, any other questions? Okay. Good. Let's go talk about the angle bisector theorem. Are you studying your notes every night? That's how you get familiar with the subtlety. Here's what I mean. The subtlety but critical information was this. And if you don't read your notes, if you don't even remember this theorem, then it's difficult. Here's what it said. Any point on the perpendicular bisector is equidistant from the endpoint of the segment. The converse, meaning if we go backwards, is also true. So if you're not given that enough information to see that for sure, then this doesn't hold. And that's going to be true of this theorem as well. Okay, angle bisector. So now we're splitting an angle in half. If a point is on the bisector of an angle, then it's equidistant from the two sides. So if this AD is bisecting angle A, and it shows that it is, then point D is equidistant from the two sides of the angle. Now, my question is, there is not a word in there about it being perpendicular, so why are those shown? Why are the two little red boxes shown as perpendicular if it doesn't mention that at all? Yes, but why? Have you ever heard the saying, the shortest distance between 2 points is a straight line? You ever heard that before? Okay, so take that and add to it, because that's not sufficient. The shortest distance between 2 points is a straight line, yes. Like, I'm not going to like curve my way over there. But also at a 90-degree angle. So for example, take this and compare that length. That's a straight line. But which is longer, the purple or the black? The purple is longer. So even though it's a straight line, it's not the shortest. So when we stick that 90 on there, we're saying go directly to the line, don't angle some weird direction. Okay? Now we're comparing apples to apples. And it's equidistant means these are the same length. If we didn't put the 90 there, maybe you draw your line here and I draw my line up there, and it's like, well, no, those are not the same thing, right? You can't, you have to have a direct path. Okay. This is the converse, which just means read it backwards. Remember that from yesterday? So read the language. Here it would say, if it is equidistant. If it is equidistant, then it's a bisector, or it's on the bisector. Okay? Then it's on the bisector. Converse just means read it backwards. Those are both true. That's what we're saying in this. Again, we're going to plug this in and use algebra just like before. I have enough room there. Make it work. Okay, a little section break just because I don't want you to confuse these, even though it's basically the same idea. Similar idea. that is a D. That looks like an O. Alright, so go ahead and get that picture drawn in there. And I'll wait for a second. We'll write the words, but then I think I don't want you to miss problems because you make assumptions. So here's the words. If a point, and in our picture it's point D. Point D is on the angle bisector. And the angle bisector here is BD. Then it is equidistant from the sides of the angle. And so that would be BA and BC. Do we have that notated in the picture yet? I mean, I don't, so we need to put that in. But I want you to be clear, none of that, what we just wrote, is in here, okay? So here's what I want you to kind of cue yourself. If we know this, that the two angles are congruent, then this is true. Okay? So if that is an angle bisector, then the two distances are congruent. I see people looking. Let me raise that up a little. Okay? And then the reverse is also true. So the converse, reverse is also true. In other words, if you know the blue, then the red, then the green is true. So on these notes, I want to make sure that you know what you have to see in order to use the theorem. Just because you see this like diamond, like arrowhead shape doesn't mean it's angle bisector unless the conditions are met to use it. So we have to know one of these. We could do that on the perpendicular bisector too. Like if you know this, then this is true. Or if you know this, then this is true. Do you want to do that, or are you good? Hi. Do you need
if I grab a couple names?
Sure.
Isla, Carmen, last name.
Okay, so if, do you want to go write that? If these are true, this is true, and vice versa? Yeah.
Is the converse true on like everything geometry, or is there
It isn't always. Yeah. Good question. Yeah, sometimes when we read it the other way, it changes the conditions. So it isn't actually true. And it's usually has to do with specificity. Like all rectangles are parallelograms, but all parallelograms are not rectangles. So that kind of thing. So if we said the reverse wouldn't be true. Yeah.
What does that say it is?
Where?
After
Do I need to scroll?
after the bisector, then it is.
Equidistant
Okay.
from the sides of the angle.
Thank you.
Yeah. Alright, well you guys let me know if you change your mind on that. Okay, so let's look at some problems. Are the conditions met to apply this? That's your first question. Do we know if we can use the angle bisector theorem? It looks like an angle bisector picture, but do we know if we can use it? Yeah, Tim says yeah. What tells you that it is okay? How do you know it's an angle bisector? Because what? Well, that just makes it look like it is, but something in here tells us for sure that we cannot debate. It is for sure that.
There's the two right angles and the congruent angle in the
Yeah, the right angles actually don't matter. I mean, they matter, but they don't tell us it's an angle bisector. So then what'd you say?
and the congruent angles are like
It's these right here, okay? So that tells us, these tell us it's an angle bisector. Why? What do those notations mean? What do those little arcs mean? It means they're congruent. Congruent means bisected. It means split in half. Right? If you cut your sandwich in half and I can tell you, hey, those are exactly the same size, you know you split it in half. That's what those little arc marks tell us. Okay? So then to solve, because that is true, what else is true? I want you to think through the logic process. Because this is true, what else is true that would allow us to solve?
KL and LM are congruent.
Yeah. KL is congruent to ML. Because this is true, then KL equals ML, and therefore we can just set them equal to each other, and now we have this nice easy algebra equation to solve. Okay, just curious on your opinion. Most of the algebra solving in this entire course from now till Christmas is pretty easy, most of it. But do you see where the complication comes in? Which is, which theorem, how do I apply it? Which theorem, how do I apply it? So that's why I keep telling you, study those notes, study those examples so you get familiar with what they look like. Because like this you can do in your head, right? So subtract 2, add 11, and we get x equals 7. But that is not what the question asks. What does it want? KL. So how do we get KL? Yeah, plug x equals 7 into the expression there. So this is 17. Alright. That was a good one. Let's do another one. Well, before we do these, would you like to put an example, or can you just go back and look at these? I mean, the concept is know the theorem. That's really all, right? The geometry or the algebra solving is easy. So, example or not? You see a no? Okay. I'll give you a minute to do. Guys, basically these problems are playing around with your understanding of the conditions of the theorem. Okay? So the angle bisector theorem says if a point is on the angle bisector, it is equidistant from the sides. So in here we're told HI and IJ are both 7. So for the first one, we're told this is true. So basically we're working with the converse. We are just told that the point is equidistant from the sides. Okay? Now it tells us that HGI, angle HGI is 25. And it wants IGJ, this one. Well, what do we know? Because that point, it's kind of an interesting progression. Because this point is equidistant, it tells us that this line is a what? That GI is a what? Angle bisector. Angle bisector means that this angle and that angle are what? Are equal. So that makes that 25 degrees also. So there wasn't really any calculating, it was just knowing what the theorem says. Okay, now we come in here and say HGJ, that's the whole thing, is 57. IGJ is 28.5. Let's do this. I'm gonna grab another one of these pictures so I can write on it twice, that's all. That way we don't have to lose the first one. Alright, tell me about this next one. If HGJ is 57 and IGJ is 28.5, what does that tell you about this angle? Yeah, and by what geometry concept do we know it is also 28.5? AAP, right? These have to add up to the total. So by the AAP, this is 28.5 also. Okay, so what did that just tell us? In a roundabout way, what do we know about this GI in this problem? It is a angle bisector. So now what do we know about, H, we were told HI is 12.2. What do we know about JI? 12.2. So it's cool because we don't have to do any calculating as long as we know theorems sometimes, as long as we know the condition of the theorems. Okay? Alright. How do you feel about that? Seem okay? Alright, that's the end. So why don't you grab your paper, the one that we were just checking. And I'll tell you which ones to do.